Previous video, we've seen the curve that goes like this, right? What this would look like, and honestly, this is still an increasing function, right? We're not discounting what's going to happen afterwards to drop, right? This is still an increasing function. And there's actually a difference in the way we approach an increasing function and a decreasing function. In an increasing function, we can use a cobwebbing, but in a decreasing function, it's a little bit different. So let's take a look at what's the major difference. So we have two graphs here. So we're going to take a look at graph number one. Then you start from x naught here. Let's start from 0 here. So remember, the way we do this kind of same thing, right? We go to our f function, and then we want to draw a horizontal line. So it touched our y equals to x, right? Because our y input here is going to be the x input for our next term, okay? If you don't really understand what this means, but what we're doing here, feel free to check out our video 2, the part 2 series. So this one goes down, it actually goes back up, goes up here, do this, do this, do this. And if you repeat this multiple times, you would eventually get a value here, and this becomes our x hat, which is our equilibrium. So this is what we call a stable spiral. And the reason you see that it's an unstable spiral, so let's say I have an x naught here. All right, so forgive me, I have to redraw the graph again. So let's start from x naught here, it goes up, right, it goes like this, here, 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 here. It just doesn't converge to a point. Whereas here, right, on our left-hand side, it converged, but on the right-hand side, number 2, it doesn't converge. So this is what we call an unstable spiral. So stable spiral and unstable spirals kind of had the same concept with our stable equilibrium and our unstable equilibrium. So I hope that makes sense. So the million-dollar question here is actually, how do we actually define and know that, without drawing, that it is a stable or unstable spiral? And the way we kind of solve this problem is actually the same for both increasing and decreasing function. So let's take a look at here. So let's take a look at here. We are trying to find what we call the stability criterion, right? What defines a stable and unstable equilibrium. So first of all, let's look at our point A here. Our point A here, if you remember, it's a very steep slope, right? It's a slope like this, and B is a slope like this. And let me just give you the idea, the fundamental idea is that f prime, right, B, if it's less than 1, then it is stable. And if f prime A is greater than 1, it is unstable. So because our f prime B, right, is less than 1, the slope is less than 1, so it is stable. But f prime A, you see that the way it kind of, you see the steepness of the slope, right, is greater than 1, so it is unstable. Actually, same for the decreasing function. The reason why we can do this, okay, a stable spiral, is because here, right, our f prime x hat is actually less than -1. Okay, it's going down, so it's negative, right? So here, you can see that we're spiraling out of control. It is because our slope, our f prime, at our x hat is greater than -1. So what we can do now is we understand, okay, so we have this and this. We can actually combine them together. And by combining together, we can actually find that our f prime x hat, right, has to be, number 1, greater than -1, right? And it has to be smaller than 1. And so we can actually build on this concept and basically say, okay, we take the absolute value of f prime x hat, and we have to make it such that it's less than 1. So this is our criteria. How do we determine if it's stable or unstable? As long as our absolute value of our slope of our equilibrium is less than 1, then this one is stable. So kind of sum up with what we have been talking today. So let's look at a question from our textbook. Basically, it's built in the context of modeling fishery populations, right? We have to first find the equilibria and then determine the values of C, which they're stable. And at the end, try to guess what C means along the way. And at the end, I will review that as well. So let's start by finding the equilibria. To find the equilibria, well, first of all, we need an x hat, right? X hat equals to our C x hat e to the power of the negative x hat. I'm just replacing all xt plus 1, xt, whatever, to just x hat. Okay, this is what I'm doing. And to continue moving forward, we actually just want to find x hat, right? I want to know what's the value. If we move this x hat from the right to the left, we'll get 1 anyways. So 1, CE negative x hat, right? What happens is, okay, we have E here, so we have to take a natural log on both sides. Natural log 1, natural log C plus natural log E to the negative x hat. That's what we have. And eventually, natural log 1 is 0, natural log C minus our x, okay? And we have this one here, so we know that, okay, to find x hat, so we know that this one here, so all we gotta do is just put x hat to the other side. X hat equals natural log C. So we found this. This is our equilibrium. But at the same time, we don't want to forget that we also have another solution. Equals, we have x hat equals to all that. So all we gotta do is just make sure that we're changing x hat to 0, right? So that if this one also to 0 and 0 equals 0, everything kind of balances out, right? So don't forget that x hat equals to 0 is also a solution. So 0 is an equilibrium, as well as x hat equals to natural log C. It's an equilibrium. Okay, so we found the two equilibria, and now we can go to step 2, where we want to determine the values for which they're stable. So we know from our equation that our absolute value of f prime x hat, right, it has to be less than 1, which means that our f prime natural log C has to be less than 1, the absolute value of it. So we can actually just quickly find the f prime x here. Just for simplicity, I'm not going to write xt, I'll write x, okay? I'm going to write this one. So we have ce minus x plus our cx e minus x. And then because there's product rule, we change it to minus over here. And then we can take away ce minus x here. So we have 1 minus x. So this is our f prime x. So finding f prime ln c natural log c is our first step, right? So all we gotta do is substitute e negative natural log c times 1 minus natural log c. And basically that is equals to ce natural log c negative 1, right? Because we're doing this with our logarithmic properties. And then times 1 minus natural log c. And all that because of the inverse function, it's just going to be c over c, that's 1. And 1, we actually just can forget about it. So f prime natural log c is just going to be 1 minus natural log c. Okay? And we want to find f prime of 0. So f prime negative 0 is just going to be ce negative 0 times 1 minus negative 0. And all that is just going to be c. So we found a slope of tangent at natural log c and at 0, and they're both equilibriums, right? So now we want to know if they're stable. Again, we just continue. So because of the stability criterion, we know that f prime natural log c is going to be, the absolute value of it is going to be less than 1. And so this just simply means f prime natural log c is going to be less than 1 and greater than negative 1. And now, and again, now we can just substitute this one, right? So we have negative 1 less than 1 minus natural log c less than 1. And now we can do, first of all, the first step here. So let's do negative 1 less than 1 minus natural log c. So what we're going to get is, here you have negative 2, negative natural log c. And when we do this, we want to switch the sign for the inequality, and it's e squared greater than c. Okay, that's our number 1. Number 2, we want to do these terms here, right? 1 minus natural log c is less than 1. So we have 1 minus natural log c less than 1. Then we have 1 minus 1 is 0. And then with natural log c less than 0. And then so we flip the sign, natural log c is greater than 0. Okay? We're not done, obviously. So we're just going to make c here, and then e to the power of 0 is going to be 1. So combining all of this, we have the ultimate formula of c is greater than 1 and is less than e squared. And again, because of having that stability and stability criteria, right, you can find that, okay, when c is within this boundary, it is actually stable. So we've actually found what we're looking for in the question, which is to determine the values for c, which they're stable, and we have this here. So conversely, if we're looking for the values of c which are unstable, all we gotta do is just flip everything, right? So we have, if our c is greater than e squared, right? We know that it's going to be unstable. And if our C is going to be less than 1 or less than 0, then we know that it's going to be unstable too. And so the reason why I add 0 here, because it kind of goes back to what C is, which is why I asked you guys before starting this question, what C is. C is basically what we call the intrinsic growth rate, right? Growth rate, or the maximum reproduction rate, which is kind of like the small r that we talked about in our last equation, right? Reduction rate. So it can't be 0. It was given here, right? C greater than 0. Okay, so this is the boundary. So this is the boundary when C is unstable, and this is what we're looking for, which is the boundary when C is stable. So I hope this all makes sense to you so far. And this is the end of videos, and I hope you enjoy learning, and stay tuned for more. Thank you.